Okay, we'll make a start. We'll make a start now. So today we are going to look at material properties. So far we have looked at if a given set of forces are applied on a structure or a part of it, then how that force ultimately finds its way towards the other parts or to the ground in many cases where the load would be resisted. So by the process of that, we have looked at how it will stress different parts of the member in different ways. For example, load can go directly along the axis of the member, creating tension or compression as in truss, or it can cause bending and shear. So today we look at how the material possibly could cope with that. Now, to do that, we need to know a little bit about the material, key material properties that we'll be looking at later to compare the effect of the loads. So I'll stay with fairly broad definitions of the material properties, primarily here mechanical properties of material. Now you have done, or you are already probably doing, or will do 2 or 3 units in materials where you learn quite a lot about material properties in detail, but here we'll concentrate on the mechanical properties. So if you do want to know what is the strength of a material under tension, for example, or how it will fail, you take a sample of that material and put it in something called a tensile testing machine. And middle part of that specimen is uniform cross-sectional area, and the ends are a little bit thicker so that it can be held on to sort of a jack in the end or a clamp at the two ends, but also it doesn't fail at the end. So you force the failure in the middle part of the specimen. So I'm going to show a couple of videos in here. Okay, so interesting things to note here is few. One is you could see the failure happens at about 45 degrees roughly to the length. So it didn't snap off.
Isn't this 45 degrees because of propagation of, I think, something like cracks along the planes of principal shear? Because the planes of maximum shear are 45 degrees to the direction of the loading.
Yeah, that's absolutely right. So these are mild steel specimen, so they will ultimately fail by shear, and the shear plane, as you correctly said, at 45 degree to the directions of this one. Now we'll not go into that detail. So how the shear plane and the tensile loading plane in this case differ by 45 degree. You look at it at a later stage in second semester and also in some cases year 2. But that is one thing to note. Second thing, just before it fractures, you can see this cross section here reduces. So here cross section is this much, and there just before it snaps, you will see that there is this piece is called necking. So the cross section reduces in diameter in this case. Okay? And if I show you the load deflection curve, then you could see that the initial bit has got fairly linear behavior up to this load 50 kilonewton for this specimen. And then there is a little bit flat part. The load does not increase, but the deflection increases. This is called yield plateau. So what happens is, at this load 50 kilonewton, yielding happens. Now, when you do the material unit, you'll understand what yielding means. It's the rearrangement of the slip planes. So they slide past each other at that load, and then you'll start to get a quick displacement without any increase in load. And that happens at here, called yield plateau. And that, how much it will do depends on whether the material had been stressed to the yield before or not. So if this is the first time this is yielding, then it shows a larger yield plateau. But if you have yielded it, taken out the load, and then put the load back again, you will not get a sharp or distinct yield point like that. And then what happens is the material plane slips past another, and then ultimately at a point, say let's say in this case about related at a point when vertical displacement is 10 millimeter, they start to lock up again, and the load starts to increase. And finally the failure happens at, in this case, about 65 kilonewton load. Now you could see the amount of displacement this mild steel specimen goes before it fails. In this case, the dimension was, if I go back here, dimension was 460 millimeter length, and 12 millimeter was the diameter. So if you see that before the yielding happens at a very small load, so small deflection. So yielding happens at a very small deflection, about 3 millimeter deflection or displacement in this case. But the final failure occurs in almost about 10% increase in the length. So 460 millimeter, so about 46 millimeter displacement would be 10%. So that is about here. So it increases for this specimen about 10% of its length before it finally fractures. So that often gives people enough warning when a mild steel specimen is likely to fail. And this behavior is called ductility or ductile behavior. Not all specimens are like this. Some of them fail very quickly without much of a warning. They are called brittle material. So few things to point out here. This bed, linear elastic bed in here. Now I didn't define elasticity so far, I'll do that. But the first linear bed, it will go up to the point, and that is the yield load. And then you have got a yield plateau, and then strain hardening, and finally failure. Now if you had a thicker specimen, not 12 millimeter diameter, but 24 millimeter diameter, then you will get a different set of curves. So possibly with a higher load in this case. So that really doesn't give the material property uniquely. So what we normally do in engineering ways, so if you do a big specimen, you could get, say, a force versus extension in this way. If you take a small specimen, small I mean smaller diameter, not the length. So if you take a small diameter one, say we tested 12 millimeter, if you take 6 millimeter diameter, that will of course carry less amount of load before it fractures. So you could get behavior like that. Now, that doesn't really say things about intrinsic property of material. So much better way is to be done by what Thomas Young proposed, is instead of plotting load versus deflection or displacement here, you convert the load to stress. So you divide load by the cross-sectional area, because the load is acting perpendicular to the cross-sectional area. So more cross-sectional area means it can take more load. So if you could normalize the load with respect to the cross-sectional area, then you get the stress. And also, instead of plotting the extension or displacement, you plot the strain. How do you get the strain? You divide the extension over the original length. So in this case, original length was 460 millimeter. So you divide each stage the displacement with respect to the original length. And that, if you plot instead of the load versus displacement, both of those big and small curve would come out to be nearly about the same if it is made from the same material. So you'll see, instead of plotting load displacement, if you plot stress and strain, they will tend to fit into the similar sort of curve. So we plot stress versus strain, not load versus deflection. The machine would give you load versus deflection, that is right, displacement. So you then need to convert that by dividing the load to the cross-sectional area and dividing the displacement by the original length and plot that to get the material property. So if you do a plot in terms of the stress versus strain, then the first bit would still be linear, and you'll get an yield point, and then you'll have got an yield plateau, and then strain hardening, and some necking, and then the fracture. Now, what we mean by elastic is, if you take away the load, it comes back to the original position. That's elastic. So if you are loading the specimen and the stress is increasing and so is strain, let's say you are halfway up there. And now, if you take away the force, you will come back along the same path back to the original one. It's almost like if you push this foam specimen, and if I take out the force, it comes back to the original shape and form. But if you go beyond this yield, that doesn't happen. So if you go beyond that point, and if you release the load, you'll come back to the zero stress position in this case, but it may not have come back to the same shape. You could have some still residual deformation in this case, or plastic deformation.
Wouldn't that also lead to an increase in the yield strength of the sample?
It could when you do the next time round, yes.
And this is why we use that. And this graph shows the main reason why we use that for fishing rods. When you unload, you basically got yourself a new elastic graph.
Yep.
You technically got yourself a new apparent yield stress.
Absolutely.
This is why people pre-stretch fishing rods before selling.
That's good, but I'll try to get you for that example paper clip or something. Okay, I've got one. Found one, not quite paper clip, but something similar. So this is this has got a metal bit inside it. So if I bend it a little bit, leave it almost similar shape. So this is a little bit of thing. So if I bend a little bit, leave it, it comes back. But if I bend it hard enough, it doesn't come back to its original shape. So what happens is a permanent deformation forms. So a permanent deformation forms, so this metal bit forms a permanent deformation. Now, it would be much more prominent if it was, you could see this so if you now try to straighten it, say I want to straighten this bit, this has got a kink in it. If I try to straighten it by bending it another way, you can never do that quite, you cannot see that, otherwise you will see that you cannot, it's only the rubber, it is showing that other way. What will happen is, it will form another dent, another kink next to it. So you cannot really bend it back, which he is trying to say that it will form. So if you have gone up to this point, for example, and you have come back, you will have some permanent deformations. And then if you start loading it, you have passed the yield point. So you need to go up to here to get it yielded, for example. So nearby point might start to yield, which has not had that previous excursion to yielding. So take a metal paper clip, bend it. Unfortunately, this is plastic, so I couldn't demonstrate it very well. So take a metal paper clip, bend it one way, and then so that a permanent deformation forms, and then try to make it straight. So you will invariably come up with two kinks in the opposite direction, two bend in the opposite direction next to each other. So it will be almost impossible to make the initial bend to a straight one because of this property of strain hardening, okay, which he is trying to, he mentioned it just now. Okay, so necking, we said that it happens because the cross section reduces at certain stage, and that's why the stress starts to fall. But actually the stress doesn't fall. The load doesn't fall. Stress does, because we divide the load by the original cross section. Now if we did take into account the reduced cross section for this part or for all the parts, then the stress would increase until failure, as did the load in the previous case. So for our part, this initial part, linear elastic behavior, would be important, and the slope of that, the gradient, we call Young's modulus of elasticity, and that is often shown by the Roman letter alphabet, capital E, and the small e is the epsilon, the Greek letter epsilon. That's for strain. And sigma, Greek letter sigma, is here stands for stress. So the stress is equal to Young's modulus times strain. So that we will be using again and again, stress equal to E times epsilon. And that linear behavior is what we will be using for most part of the course. Now, not all the materials will have this linear elastic behavior. It could be non-linear from the very start, but we take assumption in many cases so that the calculations are easier. So I'll show you one material which doesn't have that behavior. So let's say, for example, concrete. So you could see that the load versus displacement behavior in this case is anything but linear to start with. It's very different to the steel, that mild steel one that we've shown. And also, from the peak load, it doesn't stay far. It quickly fails. And the displacement is also at failure is not much. So this is a typical example of brittle material. Initially, there is a bit of a flat bit, and then it starts to pick up. That flat bit is possibly due to the platen coming into contact with the top surface and bottom surface. And they are not they are not exact contact to start with. So initially, there will be some amount of displacement to accommodate that any unevenness on the platen surface to the top or bottom surface of the concrete. So that unevenness is makes it this bit flat. And then when they are in properly contact with each other, then you'll start to see the load and displacement increases proportionately. So if you have to calculate Young's modulus for concrete, you take into account this bit here in the middle, okay, rather than the initial bit here. So when you do a real specimen test, these are the things that you need to do. So don't assume if you do a concrete test, you'll get a nice graph as a linear graph from the start. You can have behavior like this first, and then to get the Young's modulus part of it, that is, you need to take the middle portion of it. The other part which I wanted to show you is here. Now, the concrete, you are putting the load in the vertical direction. So the load is coming from the two directions, from the top towards the bottom. So if I show you here, I have got a bit of a. So you are putting the load. So you are putting the load in this direction. So I am compressing it in these directions, for example. Okay, I am compressing it in this direction. So how it is failing? Now that bit, if I go back again to the test sample, now if I look at slowly, so the load is applied in the vertical direction. So it is compressing. And see, when the first crack appears, let me take. Now, can you see this side has started to bulge a little bit outside? So if I take one frame back, can you just see that it is trying to bulge towards the side a little bit? Look at a little bit more carefully. So it is bulging towards the sideways, you could see. So if I take a frame by frame, and you could see the crack starts to appear here. And the crack starts to appear in the vertical direction. So normally the crack would start, so you are applying the load in this direction, crack is appearing in this way. So what would cause a crack? The crack would cause a tensile strength. So you are trying to pull it apart. So by applying a compressive load in the vertical direction, you are almost creating a tensile stress into the strain into the lateral direction. So a force in this direction in the compressive way is creating a tensile or the lateral direction, a tensile strain. And this is very important, and that's how many of the materials which are weak in tension, like concrete, they fail. So if you somehow stop that to happen, so if you make them not to expand on the sideways, then they will take higher amount of compressive forces. So because concrete is weak in tension, and if you apply a load compression in this way, it will try to expand lateral direction or tension in the lateral direction. So if you can stop that lateral expansion, this material will take higher amount of load. Now these lateral expansion due to this is due to the load is called Poisson's effect or Poisson's ratio, how to calculate it. Now, it happens in tension as well. So if you take a specimen, you load it under tension, then it will elongate under the load. That is true, but it also will reduce in cross section. And reverse thing happens for this concrete case. You are pushing it down. It's a compressive force, so it will fatten up. It will expand laterally. Unlike this case, it is contracted laterally if you have got the tension. So this ratio of the lateral strain versus the original strain that you applied is called Poisson's ratio. And this Poisson's ratio is shown by this Greek letter nu, and as they are of opposite direction, that's why the negative sign. So epsilon y, which is the lateral direction, would be minus nu times epsilon x. So if epsilon x is positive or tensile, then epsilon y would be compressive. If epsilon x, which is this vertical direction, was compressive, then epsilon y would be tensile. Now, most of the material behave in that way, but in fact, all the material would behave in that way. But this experiment, this project, one of the undergraduate student did a couple of years back. I put her thesis on that. And some of the biological structure could have structure, I mean the internal structure, such that this Poisson's ratio could be positive in that sense. So that doesn't make sense in this case. But these are called auxetic structures. So she made quite a number of these structures, different pattern. And what happens is if you put a stress into them compression, this side compresses. And if you extend, this will extend as well. So it's a positive Poisson's ratio. Got loads of applications into the impact resistance. For example, car bumpers and the other things, for example, or landing gears. So these auxetic structures is quite a active research area, and to come up with different form of structures, so that gives the Poisson's ratios as positive. Poisson's ratio is negative for the material point of view, but you can arrange the material in a certain structure. I had a paper model which I could have demonstrated that effect to you. I'll bring it to the next lecture. I couldn't find it this morning, where if you pull it, then it will expand in the sideways, unlike the concrete that you have shown. And if you compress it, then it will also compress on the sideways. Okay? So these are called auxetic structures. Okay? So how does it relate to these other things? So you could say energy is load times half load times displacement. That's related to elastic energy per volume is half sigma times epsilon, half E epsilon square. So that's the energy that it will go through. Now this bit probably not very clear to you, so I'll probably do just. So imagine you have tested a specimen. You have tested a metal specimen under tension load. Thank you. I thought I did, but I didn't. So imagine you have tested a specimen under tensile loading, and the length of the specimen is say L, and the cross-sectional area is A. A is area. So you put it in the tensile testing machine, and you put load, and due to this load, this material will elongate, okay? So the material will change its length. So the material will, this will change in length. So you measure the elongation. So the elongation, so material elongation is say delta. That means the length become L plus delta. Okay. So the original length was L, so that changes to delta. So if you plot what is that one, then you will get a behavior something like this up to the yield, and then the yield plateau and those other behavior. Now if you convert that into stress to strain, so the stress is given by sigma, which will be T over A, and the strain is given by delta, is epsilon, which is given by delta over L, original length. Then you'll get this sort of a behavior, and this is called yield strength. That means at this point the material yields. So what happens to the energy? So the energy, as you know, energy is load force times displacement. But in this case, force and displacement both are varying at the same time. So the work or energy would be, so this is work or energy, you could say, same thing, is equal to half, if this is T, and if this is delta, half T times delta. So the machine did work of this much, and that is stored as a strain energy within this bar. So like a spring. So although you don't see so much of an elongation, so the machine worked half T times delta, and that energy is stored as a spring or a stretching energy within that bar. So as soon as you release from the machine, that would come back to its original shape. So material would shrink and come back to its original shape. So when it is at the elongated state, the bar had this much of energy stored in them. So the stored energy is called strain energy. So the stored energy, when it is at the stretched state, is called strain energy. So the material has strained to get that strain energy. So what is the strain energy? That's exactly, if there is no loss, that would be the work done by the load, and that has got to be stored, that is stored within this material as stored strain energy. Now, there is one quantity we often like, is strain energy per unit volume of the material. So strain energy per unit volume. So we know strain energy is half T delta. That's the work done, same as strain energy. What is the volume of this material? The length is L and cross-sectional area is A. So the volume is A times L. So if I just rewrite this little bit and divide T over A and delta over L, then strain energy per unit volume is, now this is stress and this is strain. So half sigma times epsilon. So if we know the stress and strain due to certain forces, then if I multiply them and divide by 2, that will give me the strain energy per unit volume of that material. And if you multiply by the whole volume, then you will get the total strain energy that has been stored. Now what happens if the stress and strain vary from point to point? Then of course you do this multiplication by the volume in the local volume, and if the stress at different points is a different value, then you multiply with the local volume, and then that will give you the total strain energy. And then if you add all the volumes, then that will give you the total strain energy, which must be equal to the load, work done by the load. So the work done by the load here is no difference, force times displacement, but only with a half sign. Half sign because the load and the displacement increased from 0 to the final value. So the load was not at a full value and then displaced delta. So the load started from 0 and increasing load increased the delta. So you need to find out the work done due to this load. So that gives you the idea of the strain energy in this case. And if you want to convert that into only strain using Young's modulus, you could do that. Or if you want to do just in terms of the stress and Young's modulus, that also you could do. So that would be useful quantity for us as well. So in one of the methods that we'll be learning is if we want to find the deflection, for example, or a displacement, you could find out how much is the work done by the load. So half T times delta. So a delta bit you are interested in. And if you know somehow to calculate this elastic energy, strain energy, then you can equate those two multiplied by the volume appropriately. Then that will give you the delta. Okay, so there are various methods related to that. We'll look at that. Now, after elastic bed, many of these material fell. So we have shown you for the concrete, but other things like carbon fiber, glass, they also fell. So two of those, carbon fiber composite and high tensile steel, I'm going to show you. So you could see carbon fiber is very strong, or in terms of the strength is very high, carbon fiber composite, but it's very brittle. It almost gives no indication that it is going to fail, and failure happens very suddenly, and you could see the pieces flying off. So it's a very brittle type of failure, similar to the glass, for example, structural glass. So I've got some video of structural glass done in the Parisal lab. So I'll put that in the blackboard for one of the students that we did. And you could see that it flies off in a very, very brittle manner. So these are type of examples of brittle failure. Now, if I show, we've shown a mild steel bar, but if the material is high tensile strength, similar diameter, 460 millimeter length, 12 millimeter diameter, but this time the bar is high tensile strength, and see how the behavior changes. So if I stop at this point, you could see that it increases, this is probably the yield point, but although the specimen had the same length, about 460 millimeter, the mild steel bar failed at about 50-55, it displaced before it fell. This one is much lower displacement, so it failed about 1/3 of the mild steel specimen. but the load capacity is higher than the mild steel. So the steel, when you make high tensile strength, when you increase its strength, you increase the carbon content of the steel. And carbon content increasing makes it much more brittle as well. And that's what happened. So it fails at a much lower displacement. Okay. I'll just see whether we have got any glass here or not. But, so this is structural glass that fails under an incremental load. So that's from a point, and you could see the brittle nature of it. And if I take it to, but I've got slightly better, more sort of better videos for structural glass. I'll show it to you next time. No, these are rubbish video. Okay, thank you. So some materials are weak in tension and strong in compressions, like concrete, like cast iron, and like carbon fiber composites, for example. So not that way, carbon fiber composites, they are weak, not as in a concrete way, but they would have different tensile strength as opposed to compressive strength. So they could be different. Okay, so what happens if that's the case? Then you reinforce them. So you put fibers in carbon fiber composites is to increase its tensile strength, for example. So concrete is weak in tension, you put reinforcing bar in them. So that will take the tension, the bit of the weaker component of the strength. And that increases for their usability. You could apply them to everywhere. They could be expected to resist both type of forces, tensile as well as compressive. I think that's about it. Other aspect which I could say, other type of effect could be, for example, fire. And fire makes most of the material to expand. Now if it is free to expand, then there is not stress in them. But if you restrict that expansion because that member is connected to another member, or it is connected to ground, for example, or other supports, then stress would be generated. It's almost like those classic pictures of a railway track buckling on a hot summer day type of, that is again thermal buckling. So again, this sort of things fails. Twin tower collapse in 9/11 is primarily the failure due to fire. So in terms of the material behavior, important quantities that we need to understand is the Young's modulus and the yield strength. And the Young's modulus would lead with the unit to calculate buckling and the other parameter, as well as the stress and strain to the force and displacement. And yield stress will of course relate with the strength, and the collapse, it will define that. These are some typical values of some common material. Mild steel has got about 210 gigapascal and 250 megapascal yield strength, very stiff, very strong. Concrete is about 14 gigapascal, about 1/10 to 1/3 in terms of the strength. So not very strong compared to steel. Timber similar E value for concrete, but the strengths are much lower, but depends on type of wood and construction. Carbon fiber is all higher than maybe about steel as well in terms of the Young's modulus, and so in terms of the strength is few times higher than the steel. So it's very stiff and strong, but also quite expensive. Human cartilage is very low, of course. And then why someone would be interested, but there are some papers in that. So. Then there are other type of material which are used to store energy, for example. So for example, rubber is one of the materials that is used very extensively, from a car tire to a ball to a rubber bearing, for example. And now they are excellent in taking the energy, absorbing the energy. So final material properties is the thermal expansion, comes from heating, which you have done in your physics. So I'm just restating that. So if a thermal strain is alpha times delta T, alpha is the coefficient of thermal expansion. And final point is the stress is force divided by area. So if the force can come into two directions, in the perpendicular to the axis cross section or parallel to the cross section. Parallel to the cross section, it will give the shear. Okay, I'll pick it up from the next one and do some examples on Thursday. Okay, thank you. You will get your groupings for the group work today. So those of you who still don't have a group, I'll allocate them randomly today, this afternoon. So by this evening, you will have a group for you to work with. What about the deadline? Is it 11th or whatever December was set? Is that okay? Do you have a lecture here? No?